Hello everyone, welcome back to Electronics Prepper, the channel where we try to learn as much as possible about electronics to become more self-reliant to technology and prepare for the future. In the past few months I've been trying several times to learn how to build DC-DC converters and switch mode power supplies in general, and for whatever reasons I just failed to be able to concentrate enough. I kept having all sorts of other ideas that took me in other places to other circuits, other devices that I ended up building, and I kept pushing this large topic called switch mode power supplies further away in time. But because I wanted to make a bit of a faster progress, I wanted to have some results in this matter, I decided that I should just try to build a switch mode power supply, more precisely a DC-DC converter, without actually trying to understand absolutely everything that's involved, by just following a schematic presented in the official datasheet of some specialized IC. So basically this is what I did, and this is what I want to show you quickly in this video. I searched at my favorite electronics distributor online shop. I searched for what were the absolute cheapest power management ICs, and I found two of them. One of them being this Texas Instruments TPS563201 in my case, but there are actually two different models, 01 and 08 at the end. They have small differences. I bought the 01 part because, well, it is quite cheap. If we buy 100 pieces of them, we get them for 15 euro cents per piece, so only 15 euros in total for 100 pieces. And they look quite promising. They say that they can have up to 17 volts on the input, 3 amps constant current on the output. Of course, I wouldn't actually take it all the way to 3 amps, but anyway, 3 amps is a nice threshold to have. The only problem is the output voltage range, which for some reason it's maximum 7 volts. I cannot understand why, but anyway, that's a different topic. So I bought a few of them, and yesterday I managed to actually build a circuit that is essentially presented here on the first page, and somewhere down the line in the datasheet they give just a standard a typical application. Of course they give it for some weird output voltage like 1.5 volts. I don't understand why. I changed it a bit so that I can have adjustable voltage, but other than that, it is this one that they present on page 12. So now, one bit of problem that we have with this IC is the fact that well, this IC is extremely small. It comes in SOT23-6 package. The -6 simply means that it has 6 pins. SOT23 is essentially a package that's roughly 3 millimeters long and less than 2 millimeters wide. As you can see here on the screen, I've taken a picture of the IC on a piece of paper. On this paper I had some lines here drawn. These are 2 millimeter thick lines So I mean, by comparison, you can see how small this IC is. So when it comes to working with this IC manually, it's going to be a little bit of a problem. However, if you want to make your life easier, you may choose to make use of services of companies like PCBWay, a leading PCB manufacturer with many capabilities to help you build even your most difficult circuits and projects. You can easily get an instant code for PCB manufacturing from the website's front page, upload the Gerber files, and have your PCBs created in just 24 hours. If you need more for your project finished, they offer PCB assembly services with manufacturer direct pricing, so you can have your PCBs delivered with components soldered on. This way, you don't have to do the tedious work yourself, like in this case when we have a SOT23 package. Or perhaps you just want to use the CMD stencils so you can solder the components yourself. Just finish your design in your favorite design software, upload all the necessary files to PCBWay, and you'll be contacted by one of their professional representatives after they manually review your project, offering you one-on-one customer service to make sure that your circuits get fabricated just the way you want. Are you building a circuit for a device that will need a case in the end? Then they can certainly help you with that as well, offering you 3D printing or injection molding services to have your custom-made plastic case, or perhaps CNC machining services to help you with a custom metal case. All you need to do is go to PCBWay.com, the link is in the description. Thank you PCBWay for sponsoring this video, and now let's get started with the circuit. So this is pretty much the circuit that I built. I photographed it front and bottom. Not much to say. It's the PCB layout is not the one that they recommend in the datasheet. Well, needless to say, I cannot do the recommendations for the PCB layout in the datasheet because, well, I cannot have I mean, I could have, but it would be much more difficult to work with double-sided PCB. I cannot have vias in the truest sense of the word. Sure, I could use something that looks like a via, but anyway, I just designed the PCB myself. I decided to this time not create my own coil, but rather pay for an actual coil from the market. But as far as the other components go, they are just the absolute cheapest ones. Now, the schematic that I did is this one. Okay, it's not much different from this schematic. The difference being the choice of capacitors here, both on the output and on the input, and the choice of coil. There's a certain table at page 13 that shows various values depending on the output voltage that we want. Honestly, I don't understand why we would want any voltage below 5 volts. I mean, yeah, I guess there are some digital circuits that work with 3.3. Maybe in some very particular cases we might have other voltages, but considering the maximum is 7, from my perspective, the voltage that we will want is basically 5. Now for 5 or above, they say that I need to have a 3.3 microhenry inductor, and somewhere between 20 and 68 microfarads for the output. This is why I put 233 microfarads in parallel on the output to have a 66, which is still within the 20 to 68 range. I chose to buy a 3.3 microhenry inductor, which for some odd reasons is actually more expensive than all the other components combined. Like it costs 2.3 euros a piece, maybe 1.4 if you buy 100 pieces of them at once. I don't know why, because it's not a semiconductor component, you know. Like, I imagine this IC with so many transistors inside being a lot more difficult to manufacture than a toroidal ring made from some rare earth materials, but still not semiconductor, and just some copper wire wound around it. But anyway, it is what it is. So yeah, so this is the circuit that I built, which for all practical purposes is the one in the datasheet. I've placed a semi-adjustable resistor here so that I can adjust the voltage, and it does work. Even with 3.3 microhenries inductor, you can still get to lower voltages. You don't need to swap the the coil just for that. Yeah, and that's not much to say, other than the fact that the whole circuit without the coil costs about 50 euro cents. With the coil, it will cost about 2.8 euros. That is provided that we buy all the other components other than the coil in large quantities, like 100 pieces at once. Then we get significant discount, and this is how this whole circuit will cost only 50 euro cents without the coil. Now, the IC is very advanced. Let me get to the block, the block diagram. It's a very advanced IC that does a lot of things inside. Sadly, it doesn't give us a lot of flexibility in terms of what we can do with him, because it comes with two MOSFETs, each of them having very small RDS on resistances, 95 million for the upper MOSFET and 57 for the lower MOSFET, which is nice, and it's the reason why this IC is able to go up to 3 amps. But it also means that we cannot really hack this IC, and or it would be a lot harder to hack this IC and make him work outside of these parameters that he was built for. It has two MOSFETs because instead of the so-called flyback diode, they use an actual MOSFET that they turn on when the upper MOSFET turns off, for basically much lower losses. It has a very advanced control logic. I'm not gonna go through all of the details. It has a very advanced control logic that takes into account all sorts of things, like the output voltage, the current through the inductor, temperature, input voltage, all sorts of things, and it basically turns on and off the entire circuit based on these things. It measures the current through the inductor basically by measuring the voltage across the lower MOSFET, because if we know for certain the RDS on resistance, then you know any current passing through that resistance will generate a voltage. So they use this trick to essentially measure the current through the inductor. This is why you see this line here, this wire that comes from the drain of the lower MOSFET all the way to these comparators. And they have all sorts of other tricks, like if the output is not really loaded, this control logic will basically keep the MOSFETs turned off most of the time, or especially the upper MOSFET, which is which has the function of, you know, injecting current into the inductor in order to deliver it to the output, so that this can work even with pretty much no no current being drawn on the output at all. Anyway, it's a very nice one chip fits all kind of solution. but needless to say, and it requires very few components on the outside, but needless to say, it's not so good for hacking and for making this chip work outside of its parameters. I don't think it's completely impossible, but some protection mechanisms would be bypassed if we would basically add all sorts of other things around this IC. So my best guess is that this IC is best used as he is for up to 3 amps. I would recommend up to 2.5 amps, just to be sure that you're not overdriving him. And for voltages up to 7 volts maximum, typically 5 volts, so most of our digital equipment could be powered on by this IC, well, by a DC-DC converter made with this IC without a problem. However, for other purposes, for other projects, we would have to search for a different IC and a different circuit. I've taken some measurements. I've set the output voltage to roughly 5 volts. And I've set the input voltage to about 9 volts, and I've made some measurements to basically calculate the efficiency. They already state in the datasheet that their efficiency is pretty high. However, I wanted to actually test this, to actually measure this, because, well, reality is much more important than the datasheet. And yes, I am happy to report that the efficiency in some cases in my calculations has reached 99%. I'm sure it's just it's not quite 99%. I'm sure it's just there are some errors involved in the multimeters that I used, because I basically needed to use 4 different multimeters to measure input voltage, input current, output current, and they are not very expensive multimeters, so I don't think all of them are true RMS multimeters. So when it comes to a DC voltage with a significant ripple, and I will get to that in a moment, yeah, I'm guessing some of my multimeters are not measuring quite as well as other more advanced and more expensive. However, leaving that detail aside, I've set about 9 volts on the input, 5 volts on the output, and I've measured the currents. At some point, the input voltage was dropping due to my rather thin wires that I use on the input. This is the reason why you see the input voltage dropping. At some point I had to increase the voltage of the power supply just to compensate the voltage drop on my wires per se. But anyway, that's a different story. The idea is that the absolute lowest efficiency was when I drew 100 milliamps, which is a very small current for, well, this kind of circuits. I guess 81%, it's still, I would say, pretty good. Other than that, the efficiency was pretty much above 90%. From about 200 milliamps on upwards, the efficiency was about above 90%, which I would say is pretty good. At 1 amp, 1.5 amps, which I think it's gonna be where we will be at with most of our circuits. Efficiency is around 94-95%, which is very nice, you know. Now, the one thing that I don't like very much, but it's not a problem of the circuit, I'm pretty sure it's not a problem of the IC himself, it's a problem most likely of the cheap capacitors that I used, is the ripple. Ripple is around 500 millivolts, so about 5 volts, about a half a volt. No matter how big or how small the current I'm drawing on the output. So this is pretty much with no load, and then I started increasing the load. This is one of the reasons why the switching frequency will increase. but the ripple will remain pretty much the same, around 500 millivolts, give or take. Which, yeah, it's a bit of a problem. I mean, I'm not a fan of half a volt of ripple, but like I say, it's most likely due to the fact that I used the absolute cheapest capacitors, like you see here. I will definitely, now that I have the board completed, I can definitely make some more experiments, but I will have to buy first several other kinds of capacitors, preferably low ESR capacitors, because mine are just standard capacitors that are very cheap, and you know, they're good for other projects, but not for this one. This is my best guess when it comes to the ripple that I've had, which was a bit too high. If we search in the datasheet, I'm not gonna do it now, but if we search in the datasheet, we will find that the ripple is well below 100 millivolts, at least the ripple that they say that the circuit is able to provide. And considering the switching frequency is about 580 kilohertz, well, it's not a fixed frequency, it actually depends on a number of factors, but at 580 kilohertz, yes, we can definitely have very small ripples, provided that we do everything else right. So, yeah, what can I say? It's definitely a nice starting point, I would say. It's definitely a nice solution to have in mind when it comes to you know, quickly building a DC-DC step-down converter. I forgot to mention this only works as a step-down converter, at least this is what they say. Anyway, it's definitely a good yeah, output ripple voltage 30 millivolts. See, at least in their application. It's definitely a good IC to buy in larger quantities, and whenever we need something like this, we can build one with not big of a problem. Like I said, the biggest problem is soldering this IC. I managed to do it manually. Well, I guess the picture kind of shows that it is manually. I had to use pretty much the thinnest tip on my soldering iron, and yeah, it was a bit of a work. It was a bit of a challenge, but it still was pretty fast. I mean, I haven't checked the clock, but I would say that I managed to solder this in under half an hour, which is not that big of a problem, right? I mean, we're not mass producing these things, so yeah. So this has been pretty much my first experience with TPS563201, and again, for this price, I would say it's well worth buying several components, several pieces from this component. Also, it seems to be in enough quantity on the market, right? I'm not sponsored by this company, so I don't mean to, you know, promote this company in any way, but they have right now 1,155 pieces in stock, and they are a relatively small provider which operates mostly in Europe. I'm sure that if we go to a larger provider, we will see even bigger numbers. So nowadays, small price and high availability is definitely an advantage that we want to have. So that's pretty much it for today's video. I just wanted to show you quickly some first results that I had with this IC. I'm really glad that I made this work. I'm really glad that You know, this kind of IC has a very advanced control circuitry that allows us to use cheap components, even though we get not so nice results, but we still are able to build such a DC-DC converter, as opposed to other ICs which are much more strict about what we do around the IC. You know, what's the inductor that we use, what capacitors we use, etc., etc. This is definitely a nice IC to play with and to be able to just quickly make a dirty, let's call it like this, a dirty DC-DC converter, if we just rapidly need one and we don't care that much about the ripple voltage, which is really it's the only problem that I've experienced so far. So thanks a lot for watching this video. I will put a schematic back on the screen for you to see him again. If you enjoy this, please consider hitting the like button, perhaps subscribing if you want to see more videos. I am definitely going to do more videos in the future, and I'm slowly but steadily, you know, moving towards the goal that I've described a few videos ago. So yeah, thanks a lot for watching. I will see you in the next video very soon. Bye bye.